So, in the last lecture we looked at biquadratic number fields and their rings of integers. In this lecture and perhaps the next one we will look at cyclotomic fields. So, these are the extensions of rational numbers obtained by adjoining roots of unity, and I cannot overemphasize how important cyclotomic fields are for many different reasons. So, firstly, cyclotomic fields provide you example to test conjectures that you make in general for things coming from geometry. Secondly, any abelian extensions of rational numbers is contained in a field obtained by adjoining roots of unity. And thirdly, roots of unity of course show up in lots of different places, and so often you are working in cyclotomic fields. For example, values of Dirichlet L functions all lie in cyclotomic fields. So, they are immensely important objects in number theory, modern algebraic number theory, and one should study them if you want to do number theory. So, let me define formally what it means. So, remember we are always working inside complex numbers. So, zeta n denotes a primitive nth root of 1, okay, n is bigger than or equal to 1. What does primitive mean? Zeta n to the n is 1, but zeta n to the power m is not equal to 1 for all positive integers m less than n. Okay. So, if you want in complex numbers, you can take zeta n to be e to the 2 pi I by n. Okay. So, if you want to have something concrete, you can take it this way, and then k n will denote q zeta n. Okay. So, that is my notation, right. So, these are called cyclotomic fields. And let me write down some facts that I said orally at the beginning. This is not in this course of fact, this is more or less class field theory for Q. Of course, class field theory has a few more ingredients in it. Any abelian extension of Q is contained in K n for some n. For example, if you take a quadratic extension of Q, you can always find a root of unity zeta n such that that quadratic extension is contained in this root of unity. This can be proved in an elementary fashion using Gauss sums, but it is still an amazing fact that it can be embedded this way. It's deep, okay, even if it's not very hard. Okay, so first thing to notice is the following. K n is a Galois extension of Q, right, and this is easy because you see that K n is the splitting field of x to the n minus 1 equal to 0 over Q. Okay, if you take this equation x to the n minus 1 equal to 0, then of course zeta n is a root of x to the n minus 1 equal to 0, but notice, but observe that any root of x to the n minus 1 equal to 0 is of the form zeta n to the power m for m between 0 and n minus 1. Okay, so there are n distinct roots like this, and hence Kn over Q is Galois. Right. So, we would like to understand what the Galois group of this group is, and there are different ways of doing this, but I am going to combine all this into one theorem. But before doing that, let me do the following. So, lemma, let n be a positive integer, and you write n as p1 to the r1 up to ps to the rs. Pi's are distinct primes, prime numbers. Okay. Then Kn is compositum of all these kpi to the ri. Sorry, maybe I should write it this way. Kp1 to the r1, Kp2 to the r2, and so on up to Kps to the rs. Okay, so this is a compositum, and furthermore Kpi to the ri intersected with Kpj to the rj is just q for I not equal to j. Okay, so these are distinct primes, and ri's are bigger than equal to 1. Right. Okay, so here is a simple proof of this. Firstly, firstly I will prove this thing about intersection. Okay, so okay. Right. Maybe I will postpone the proof of this to after the theorem. So, let me, okay. A later part. We first prove the following theorem. So, let me prove the let me state the following theorem. So, the reason I stated this lemma first is that it tells you to study these extensions for a general n. You need to study them only for prime powers, and once you do it for prime powers, you can deduce many things about a general n from the theorem for prime powers. Okay. And so, here is the following theorem for prime powers. So, first is that k p to the r over q, this degree is equal to p to the r minus 1 into p minus 1. Remember, this is also phi of p to the r, this is Euler's totient function. So, that is what the degree is. To the ring of integers of k p to the r is z zeta p to the r. Okay, so, everything can be written as a z linear combination of powers of zeta p to the r. yeah, 3, let m be this quantity p to the r minus 1 into p r minus 1, then discriminant of k p to the r, this is equal to p to the power m up to sign, right. So, this is plus minus p to the m, okay. And when is the sign plus 1? So, sign is plus, yeah, maybe let me write it like this. The sign is minus if p is congruent to 3 mod 4 or p to the r is equal to 4 and it is plus otherwise, okay. In all other cases it is, so if p is equal to 2, then so 2 square 4, that is the only case when you have negative sign, and in all other cases you have positive signs for p equal to 2. If p is odd, then it depends on whether p is 1 mod 4 or 3 mod 4, okay. So, that is the discriminant, and yeah, okay. So, what is the unit? So, let yeah, what are the units in zeta p to the r? Well, let us not talk about units for a moment, let us talk about the roots of unity, the torsion part, roots of unity in k p to the r. This is precisely equal to plus or minus zeta p to the r to the power s for s between this and p to the r minus r minus 1, okay. These are the roots of unity. So, there are potentially 2 times p to the r roots of unity in this. What about primes that ramify? So, p is the only prime that ramifies in k p to the r, and in fact it is totally ramified. Okay. So, if you take p zeta z p to the r, then this is 1 minus zeta p to the r to the power the degree, and the degree remember was this minus 1, right. Okay. And lastly, there is an automorphism. So, what is the Galois group? Galois group of k p to the r over q, this thing is z mod p to the r z cross. Not only that, there is a canonical isomorphism. This goes to sigma a, and what does sigma a do? Sigma a sends zeta p to the r to p zeta p to the r to the power a. Okay. All right. So, we have to prove this this theorem. We will do it one by one. Well, not always. So, some of the parts we will do at once. For example, number 5, which says that p is the only prime that ramifies, it follows from the computation of discriminant, right. Remember, we proved that a prime ramifies if and only if it divides the discriminant, and the only prime that divides the discriminant is p from 3, right, from point number 3. So, it tells you the first part of point 5 that p is the only prime that ramifies. Of course, we need to show that p is totally ramified, and we are going to do this directly, show that p is totally ramified, and we are going to use that computation to get information about 1. So, it is kind of roundabout. There are you can also do all these things independently, but we are not going to take that route. We are going to try to use some algebraic number theory, since we have learned some algebraic number theory, right. Okay, so so first of all, what is the I mean, we know that zeta p to the r is a root of x to the p to the r minus 1 equal to 0, but you can in fact write down a polynomial of smaller degree whose root is zeta p to the r. So, what you do is you consider, these are called cyclotomic polynomials. So, you consider psi of p to the r of x, this is x to the p to the r minus 1 divided by x to the p to the r minus 1, and why does this, why is this in zx? So, we will show that this is in zx, and why? So, proof of this, x to the p to the r minus 1, you can write it as x to the p to the r minus 1 to the power p minus 1, and this you can write as x to the p to the r minus 1 into x to the p to the r minus 1 to the power p minus 1 plus x to the p to the r minus 1 to the power p minus 2 plus so on x to the p to the r minus 1 plus 1, right. Hence, psi p to the r x is in zx, right. And furthermore, we know that zeta p to the r to the power p to the r minus 1 is not equal to 0. So, I can when I evaluate psi p to the r, zeta p to the r, I can evaluate it by like this. And I know that this is 0, right. So, zeta p to the r is a root of psi p to the r x, right. Now, what is the degree of psi p to the r x? This is p to the r minus p to the r minus 1, which is p to the r minus 1 into p minus 1, right. And furthermore, we know that k p to the r is the splitting field of psi p to the r x. Right. So, one field can be a splitting field of many different polynomials. So, do not confuse, because I said earlier that k n is the splitting field of k n is a splitting field of x to the n minus 1. So, k p to the r minus 1 k p to the r will be the splitting field of x to the p to the r minus 1 equal to 0, but k p to the r minus 1 is also the splitting field of psi p to the r. Okay. So, one field can be splitting field of many different polynomials, and if it is not immediate to you from what I wrote, you should try to prove that k p to the r is also splitting field of this polynomial. In any case, this gives us a upper bound on the degree. So, k p to the r over q, this is less than or equal to degree of psi p to the r x, which is p to the r minus 1 into p minus 1. Okay. All right. So, that is one thing. Now, what are the roots of psi p to the r x equal to 0? We know that psi p to the r of x is x p to the r minus 1 over x p to the r minus 1 minus 1. And what are the roots of x p to the r minus 1 equal to 0? These are zeta p to the r to the power s, where s is between 0 and p to the r minus 1. Now, what are the roots of x p to the r minus 1 minus 1 equal to 0? This is zeta p to the r p times s, where s is between p to the r minus 1 minus 1 this time, right. So, something that is divisible by p. So, hence roots of psi p to the r x equal to 0, these are zeta p to the r to the power s. Now, s is still between 0 and p to the r minus 1, but GCD of s and p is equal to 1. Okay. So, this is same as saying that p does not divide s. Okay. So, these are all the roots of zeta p to the r x equal to 0. So, coincidentally that is what you would use to show that k p to the r is the splitting field of psi p to the r. Okay. All right. So, on the one, so what this means is that psi p to the r of x, you can write it as product s going from 0 to p to the r minus 1, and p does not divide s, x minus zeta p to the r to the power s. Right? That is just the factorization of this polynomial inside kp to the r. Right. So, in particular psi p to the r 1, this is just product p not dividing s, s going from 0 to p to the r minus 1, 1 minus zeta p to the r to the s. Okay, this is this quantity, none of these factors is 0, by the way, that is easy to see. But what is psi p to the r of 1? Remember, this was right. What is this? Well, psi p to the r of x, another expression for this is psi p to the r minus 1 to the power p minus 1 plus x p to the r minus 1 p minus 2 and so on up to x to the p to the r minus 1 plus 1. So, if I just put psi p to, if I just put x equal to 1 in here, I just get p, right. Okay. So, what we have proved, so hence we have proved that p is equal to product s going from 0 to p to the r minus 1, p does not divide s, 1 minus zeta p to the r to the power s, right. All right. So, now my next claim is that the ideal 1 minus zeta p to the r s, sorry, let me write it properly. Oops. One minus zeta p to the r to the s is equal to the ideal generated by 1 minus zeta p to the r as ideals in OKP to the r. I do not know what OKP to the r is yet, but I want to show that these two ideals are the same, right, which means, so this is same as saying this is same as proving that the ratio 1 minus zeta p to the r to the s divided by 1 minus zeta p to the r is in the group of units of this ring, rings of integers. Okay. How do I show this, right? How do I show this? Well, I show that this as well as its inverse, they are both inside O k p to the r. Okay. So, 1 minus zeta p to the r to the s divided by 1 minus zeta p to the r, I can write this as 1 minus zeta p to the r 1 plus zeta p to the r plus zeta p to the r square and so on up to zeta p to the r s minus 1 divided by 1 minus zeta p to the r, and this you cancel these two, right, they are non-zero, and this belongs to OK p to the r. I do not care what the ring of integers is, this linear combination certainly is a algebraic integer, right, because zeta p to the r is an algebraic integer. So, this was easy, right. So, 1 minus zeta p to the r to the s divided by 1 minus zeta p to the r, this is inside the ring of integers. Now, what about the inverse? We can't really directly use this, but remember now S P does not divide S, right. So, there exists S prime in Z such that, or even inside natural numbers such that S prime is congruent to 1 mod p to the r, right, and this means that 1 minus, so this means, so hence zeta p to the r is same as zeta p to the r s prime, right. So, I can write this over 1 minus zeta p to the r to the s as 1 minus zeta p to the r to the s whole to the power s prime divided by 1 minus zeta p to the r to the s, and this now again one can write as zeta p to the r to the s to the power s prime minus 1 plus zeta p to the r to the s prime minus 2 and so on up to zeta p to the r to the s plus 1, which again is in the ring of integers, right. Again I do not care what the ring of integers is, I know that this is in the ring of integers, right. So, hence 1 minus zeta p to the r 1 minus zeta p to the r to the s, this is in the units of rings of integer, right. So, therefore, as ideals we have 1 minus zeta p to the r is same as 1 minus zeta p to the r to the power s. What is the upshot of all this? So, hence the ideal p OK p to the r, this is same as 1 minus zeta p to the r to the power p to the r minus 1 into p minus 1, right, as ideals, right, again as ideals. Now, I do not know whether this is a prime ideal or not, okay. Even without knowing this is a prime ideal or not, we get, so as p OK p to the r is some p1 to the r1 and so on up to p e to the re with summation ri fi greater than is equal to the degree of k p to the r q, we get that the degree of k p to the r over q is bigger than or equal to p to the r minus 1 into p minus 1, right. and a moment ago we proved that the degree was less than or equal to this, right. So, hence we get that degree of k p to the r over q is exactly equal to p to the r minus 1 into p minus 1. Okay. So, this is a good point to stop for today. We will continue with the proof of this theorem next time, and I will recall what I did today, and then we will continue with the proof next time. Thank you.